Okay, welcome to part 2 of our titration calculations. With this video, we're going to be doing two calculations. The first one is shown on the left here, but before we do that, let's just have a quick recap of the important equations we need to remember when doing titration calculations. C is equal to N over V, okay, and N is equal to little m over mR. Right, so those are the two important ones we need to always use when doing titration calculations, one or the other or both. Right, so let's go to this question here. It's a little small. If you can just pause the video and have a read of that question first. Okay, now that you've read it, what I've done is I've used the information there to draw some diagrams here to explain what's happening. So this is what I would recommend you to do as well. Right, so let's have a quick read and see how it relates to the picture. We've got magnesium carbonate reacting with hydrochloric acid, and it's an impure. It says here that magnesium carbonate is impure. We're adding hydrochloric acid, there we are, 75 centimeters cubed, 0.5 moles per decimeters cubed of it to our impure magnesium carbonate, and they're telling us that there is a 1.25 gram mass of that. Okay, some acid will be left over unreacted, so we've got excess acid. Some acid will be left over. All right. Then what they do is that they take the unreacted acid and they put it into a conical flask. Right, so the whole solution is in here. So you can imagine the unreacted acid is in here, and it's then titrated with sodium hydroxide solution. And they tell us the titer, 21.6, and they tell us the concentration, 0.5 moles per decimeters cubed. All right, so from this information, I've done this little diagrammatic thing here. All right, let's look at the first question. The first question asks us to calculate the number of moles of HCl in this volume and 0.5 moles per decimeter cubed concentration. So that should be fairly straightforward. We use our N equals C times V. So let's do that. Write down the formula. N equals C times V. And if you do that, it's going to be C is 0.5 times volume. You know it's decimeters cubed, so 75 divided by 1000, you get 0.075, and that'll give us a value of 0.0375 moles. Alright, so that's how many moles we have of our acid in here. Okay, part 2. Calculate the number of moles of sodium hydroxide used to neutralize the unreacted HCl, which is over here. So again, we've got volume and we also have the concentration. So let's work out our number of moles. So again, write down the formula from which concentration 0.5 times volume 0.0216, and that gives us 0.0108 moles. Right, there we are. That's how many moles of sodium hydroxide were used in this titration. Right, part 3. Show that the number of moles of HCl which reacted with the magnesium carbonate in the sample is 0.0267. Okay, so what we're going to do now is subtract the two values, that take away that. Right, we've got 0.0375, take away 0.0108, and that will give us our value of 0.0267. Okay, right. Okay, part 4. Calculate the number of moles and the mass of magnesium carbonate in the sample, and hence deduce the percentage by mass of magnesium carbonate in the sample. First of all, calculate the number of moles and the mass of magnesium carbonate in the sample. Right. Well, looking at our equation here, 1 magnesium carbonate reacts with 2 hydrochloric acids. So we can work out the moles of magnesium carbonate by ratio. It's 1 to 2. So by ratio, the moles of magnesium carbonate is equal to a half times 0.0267, and that is 0.01335 moles. Let's go to the next page. And N equals M over MR. We want little m equals N MR, which is equal to 0.01335 times 84. Magnesium carbonate 1 mg 24 plus 12 plus 3 times 16 will give us the molecular mass of magnesium carbonate, which is 84, and that will come to 1.121 grams. Okay, and to work out the percentage, so that's the actual magnesium carbonate in our sample. If you look back, the sample they used was 1.25. That had impurities in it. The actual magnesium carbonate is this much. So the percentage purity equals 1.121 grams divided by 1.25 times 100, and that will give us a value of 89.7%. Okay, right. So that calculation was quite involved. It looked difficult at first, but by drawing little sketches like this, you can visualize what's happening. If you take a few minutes to sort of try to understand what's going on, then it makes it a little bit easier to follow. That's a particularly difficult one, but I don't think you're going to get very many difficult ones like that. If you could do that by practice, then you're on your way to understanding the harder type of titration calculations. Right, let's try another one. Right, just looking at this one. Okay, have a read of the question. Okay, in this case, we've got a carbonate. We don't know the metal. It's a metal carbonate. The equation for the reaction of this carbonate with hydrochloric acid is given below. And you see that it's a 1 to 2 ratio. 2 HCl's to 1 metal carbonate. A sample of metal carbonate of mass 0.394 grams required the addition of 21.7 centimeters cubed of a 0.263 molar solution of hydrochloric acid for complete reaction. Again, see if you can make some sketches to see what this would look like, or just write down some information on some paper like this. And I've done that here, look. So there's the magnesium carbonate, there's the hydrochloric acid. Write down the information, 0.394 grams of your solid carbonate, and your hydrochloric acid. Let's summarize what we've got. Concentration of hydrochloric acid 0.263 moles per decimeters cubed. Number of moles we don't know. The volume we do know, 21.7. Let's change that to decimeters cubed. There we are. And as before in our normal rules, we know we can work out the number of moles. Let's do that then. Right. It says here, calculate the number of moles of hydrochloric acid. So N equals CV, and that'll be 0.263 times 0.0217, and that will be 5.707 times 10 to the minus 3 moles. Okay, fine. Now, if we know the moles of our HCl, then we can work out or deduce the moles of magnesium carbonate, not magnesium, metal carbonate. So let's do that. N equals half, it's 1:2 ratio, times 5.707 10 to the minus 3. It's also a good idea not to round off too quickly because you'll use those values later on, so don't round off until you really have to, or unless they tell you in the question. There you are, that's the moles of our metal carbonate. Okay, right, part 3. Calculate the relative molecular mass of your metal carbonate. Right, now in this question, relative molecular mass, MR, that's what we want to find out. What do we know? We know moles, right? And so the equation obviously that links those together is N equals little m over mr. Right, we need to work out the molar mass. We know the moles. There we are. And we also know the mass, which is, there we are, 0.394 grams. So rearrange this to get mr equals little m over n. That is 0.394 divided by 2.853 10 to the minus 3. And that will give us a value of 138 grams per mole. Okay, so mr equals 138 grams per mole. That's the molecular mass of our metal carbonate. We don't know what M is. It could be from group 1, couldn't it? Because it's M2CO3, needing 2 of these to every carbonate. Remember, carbonate's 2 minus, so therefore each M must be 1 plus. So it looks like it could be from group 1, but we don't know. It could be a transition metal as well, which has a 1 plus charge. Right. Deduce the relative atomic mass of M and hence suggest its identity. Right. Well, carbonate, CO3, that adds up to 12 plus 3 times 16, 48 and 12. That's 60. And therefore this must be the rest of it. Okay. So 138 is equal to M2, 2 M's, plus 60. So 2 M's is equal to 138, take away 60, equals 78. So therefore M must be 78 divided by 2, that comes to 39. That's the atomic mass. And if you look at your periodic table, atomic mass 39 is potassium. Okay, which is K. So K2CO3 was our unknown metal carbonate. Okay.